Welcome back, everyone. Welcome to my second YouTube video, where today I'm going to be talking about the PCjr cartridges and how these work. Ever since I was a kid, I didn't really know much about them, so I decided to go ahead and take a look at how they work. I apologize for the delay since my last video. As everyone probably is aware, life has a way of getting in the way of things. But we're back, and we're going to go ahead and go over this, and I've got a follow-on video planned to this as well, which I'll talk about at the end. But today what we're going to talk about is the PCjr cartridges. For instance, I have Pitfall 2 running on the system right here. Here I also have Mineshaft cartridge, and this is of course the PCjr Basic cartridge, which I as a kid of course never understood why I needed this, since the system already has Basic on it. But we'll go into that in a little bit in detail later. And some of the other things we'll look at today are how to burn your own cartridges. For instance, you can burn your own cartridges. There's different kits out there. This one I haven't installed yet, but that's Raphnet has these, so we'll talk about those a little bit later. And what we're going to do is actually take one of Oscar Toledo's games out of his book and put it on a cartridge, just for the pure fun of it, so why not? So with that, let's go ahead and get started and take a look at how these cartridges work. Okay, so to get a look at how the cartridges actually work in the system, we will open up the PCjr Technical Reference Manual. This is certainly a handy reference to have if you need any technical details on the system, although there are a few errors in it. The section on the cartridges themselves is actually under, like on page 2-107, it talks about the program cartridges, or the cartridges themselves. And the short of it is there are 15 address signals, so there is the capability to address 32K per cartridge, and of course 8 data signals, so 1 byte at a time. Then there are 6 different chip selects, which you could also use to address if you wanted to get fancy with it. And some control signals for the BIOS, and of course power and ground. So the different types of cartridges are the main type is what they call the initial program loadable cartridge. This is what most of the cartridges seem to be. And the raw data on the cartridge is basically going to start with this header of 055 in hexadecimal, 0AA, a length calculation, which is actually the number of bytes for the program divided by 512, so you've got to be in 512 byte segments. And a bytes at offset 3, 4, and 5 is going to be a jump to your initialization code on your cartridge. And then 6 is just going to be a 0, and then all your cartridge data is going to go in there, and the last 2 bytes will be a CRC. So, and I do believe if you have like your jump to initialization code can actually be shorter than 3 bytes if you need to. Just put something to fill in that 3rd byte if your jump command is only 2 bytes, for instance, which seems to be fairly common. Another type of cartridge which I've never actually seen, but apparently you can do it, is you can have a command word cartridge for DOS. So what this appears to be is actually a way to have a table of commands that if you were to type them into DOS, it would load directly from the cartridge. So for instance, you could put in your own DOS commands that go off and execute some code and then presumably return back to the command prompt when they're done, sort of like some of the built-in DOS commands that, like time and date commands you type in that don't access the disk to try to read the program. It's an internal command. So presumably you can add new commands here. I have not played with this at all, but and if anybody knows of any of these cartridges that actually exist, or anybody who's done these, please post a comment in the comment section. I'd be interested just to know if this was ever really utilized much, or if this would have been a specialty thing for certain maybe companies if they were going to use this feature. But the cartridge format here again is the same. You're going to see the same header starting with 055, 0AA, a length, which again is 512 byte blocks, your jump, and then it's going to have these command name lengths, and a character in the command name, and then the command name itself, and then a word pointing to the routine for that command. So presumably there'd just be a whole sequence of these commands in a row. Let's see. Another type is there's a cartridge basic for interpretable basic code. I've also never seen one of these. This is not the same as your basic cartridge. This is presumably if you want to put a basic program on a cartridge that the system, I assume, would load basic and then load your cartridge and start running your program immediately, is my guess based on reading this. So you get the same basic structure here, although you do get some additional at offset 3 and 4. You kind of get, in 5 even, you kind of get more of a structure as akin to, I guess, what basic is actually looking for. Because you can see here we don't actually jump into this program at all. Presumably basic will look for this and start executing it on startup. But again, if anybody knows more details about this or has ever used it, I'd be curious, so please post a comment. But again, this is not what the cartridge basic that comes with the PCjr actually does. It is actually an IPL level program like the first example. And the last one that's not exactly listed here, but that you can also do, is you can actually override the system ROM on the system. So you can actually override the 64K of ROM in the system, the boot up BIOS, with your own custom BIOS. Without having to pull chips and put your own chips in, you can actually just put them in a cartridge. And there was actually a few of these done, because there are actually a couple of minor bugs, I think, in the BIOS that were actually fixed. And there was also, I know, another modification people did, I think, back in the day to allow the system to boot up faster. The PCjr does take a while to count through its memory, especially if you have 640K installed. And there is actually a version that just completely bypasses that and just starts the system right up, so it's certainly much faster. So the cartridge slot itself just kind of looks like this. The top of the cartridge has pins A1 through A18, and here's the layout of the address lines, the data lines with the D, cartridge select lines. There's a reset tab, so when you put the cartridge in, it resets the system. I believe all my cartridges have that. I don't know if there would ever be a case of not doing that. But that's the basics of that. So the short of it is, when the system boots up, it actually goes through each of these address spaces starting at D0000 and starts looking for this header 0550AA length. And then it also looks for the rest of it to see which type it is and whether it needs to do a CRC comparison. For instance, for the IPL or initial program loadable cartridges, if it sees this header combination and the CRC bytes match up, it will jump to the initialization code here on these bytes and actually start executing the cartridge, with the assumption being here that the way this normally works is, as I said here, your cartridge is expected to set up interrupt 18 to point back to a place in your cartridge to actually start. So when it actually first calls your cartridge, the intent isn't necessarily that your cartridge should run immediately, although from looking at the disassembly of some of them, Pitfall 2 for instance, it just starts running immediately. It does not set up int18, or sorry, int18 hex. It just jumps straight into the program. Although in my own experience, when I tried to create my own cartridge, that actually created some problems, and we'll get into that a little bit later. When I tried to just jump straight into my program, some things are not quite set up yet. Although you can get around them, but the basic way it's meant to work is you set up interrupt 18, the interrupt 18 vector, to point back into your program again, and then you return control to the BIOS to finish, and then it will continue checking through the rest of the cartridges. The system ROMs do not have any sort of specific header or CRC checks. To the best of my understanding, all it's going to do is it's just going to start executing the code on the cartridge when the system boots without doing any sort of checking on it at all. So, and the other part of that is these two base 1 ROM in cartridge and base 2 ROM in cartridge signals, which it doesn't really talk about much. Really what these are these are what enable the system to have the cartridge override the system ROM rather than trying to use the internal one, and I'll go into that in just a minute. Part of me was curious once I determined that I needed to set up this interrupt 1.8 vector, is what exactly is going on and who calls interrupt 1.8. So what it really is the bootstrap loader is the one that does this. So if you look in the BIOS code in this section right here, the bootstrap loader, it basically tells you right here, if the diskette is not present or has a problem loading, interrupt 1.8 is called. So if you put in a cartridge that does this, it'll attempt to access the disk. If there's nothing in it or nothing bootable, it will just call int 1.8, which has been vectored to your program, and then your program will start executing. So that's the sequence of events that actually runs a normal IPLable cartridge if it didn't just run during the BIOS check itself, like for instance, like I said for Pitfall 2, where it just starts executing as soon as it starts checking the cartridge code. So after that I got kind of curious about how exactly the BIOS overrides the system BIOS. So I started looking into the cabling on the system itself. And Sam's Computer Facts has a little bit of information on this. So this is just the main system board diagram. And if we go in here, these are your cartridge slots. And so, I mean, everything is pretty straightforward here. It's just, 5 volts is connected. There's some capacitors, etc. Ground is connected. Your data lines are connected. Your address lines are connected directly to your EEPROM or EEPROM. And there's also these basic 1 in ROM, basic 2 in ROM connectors, which are typically left open. But if you want to do a BIOS override, for instance, what you do is, which I believe you can override either of the 32K, although I don't know anybody that would I don't know if anybody ever just overrode one of them. I think usually it was a complete BIOS replacement, but I suppose if you only had to modify one of them, you could. But you end up doing is you end up grounding some of the pins, because you have a ground provided to you in the cartridge through one of the connectors, and what you do is you ground that signal going out. And what happens is if we go over to the other diagram here of where the system ROM is, on the system board again, this is the Sam's Computer Facts page, what page is this? Page, well, 2 on this for the system board. If we go over here to the BIOS itself, which are actually these 2 chips right here, you can see that they're the cable select 6 and 7 signals are both passed here. So these are the same 2 that are passed to the cartridge for the these 2 addresses right here, F0 and F8. And so the only difference is if the cartridge grounds out this basic 1 ROM and cart or basic 2 ROM and cart, that grounds these inputs to these NOR gates and actually sends 5 volts to the pin 22 of these ROMs. And what that does is, if we look at the datasheet for those ROMs, pin 22 is the output enable or output buffer control switch. So in order for the ROMs on the system to actually drive the data, it needs both cable select and output enable to be, I believe, grounded. And so if the cartridge is instead grounding this signal, which sends a high signal to the ROM is not going to respond to those, is not going to put data on the bus when those addresses are requested, and presumably the cartridge will instead. So it's kind of interesting how that works. Although I did find it slightly odd here. I'm not sure why they used these NOR gates here and why they didn't just use an inverter or something. If I had to guess, it's just because they had spare NOR gates on the system already that weren't being used for anything, and they didn't have any spare inverters or convenience of where it is on the circuit board, but it does the same thing. And if anybody has any knowledge of why that might be, I'm not an expert in circuits, but I did find that slightly curious as to seems a little overkill. But with that, what I was going to do next is go ahead and take a look at a disassembly of some of the actual cartridge ROMs I have, and kind of go over what they're doing a little bit, just to kind of give you a quick glimpse of, you know, seeing an actual cartridge. All right, so here we're going to take a look at the disassembly of the Pitfall 2 cartridge, just a little bit, and also the basic cartridge, since I wasn't quite sure what to expect from that one. It is not actually a basic cartridge in the sense that it runs a basic program from the cartridge so much as it sets up data for BASIC to overlay commands, presumably specifically for the PCjr. But let's go ahead and take a look at this some. So I'm going to use the net-wide assembler, or NASM disassembler here. If you're using MASM, I'm sure there's an equivalent there, so the code will just look a little bit different, but that is what I'm used to. So the P16 is just to tell it it's a 16-byte machine code. I believe that is the default, but I tend to specify it anyway. And we'll go ahead and output that. And load it up. So this is what came out of it, and you can see here the entries for the IP-eligible cartridge for 55AA, which is correct. And then the next one is supposed to be the length of the cartridge in 512-byte segments. So the issue we have here, of course, is the disassembler interpreted this as code, including the 55 and AA. Those are not actual machine codes that get executed in this program. Those are just the header information, so we just kind of ignore those. But for this, the problem here we have is the fact that it offset the jump command and split it among, and interpreted it as two separate commands. So for the net-wide disassembler, what you have to do is tell it to resynchronize bytes on a boundary. So here, I'm going to tell it to align on the offset 3 byte boundary. That way we get the separation of the size entry at byte 3 or offset 3. Oops. And see here, we ran it again. So now here we can see it actually interpreted as DB20, or as a database, data byte, excuse me, entry. And that would be the number of 512 byte blocks. And now we have the jump short. So this is the program entry point, jump short 09. And again, we run into a problem where it has not aligned the bytes the way that they should be, and is not showing me what's at 9. So we go and add another one. I tried the auto synchronization on the net-wide disassembler here, and I did not have any luck getting that to work. So if anybody has any hints on how to automate this process a little bit better, it seems like the program should be smart enough to be able to figure some of this out via looking at some of the jump commands and stuff, but it does not actually. Alright, so if we do that again, and now we can see this is the actual location at address offset 9, where the program actually starts when the cartridge is searched through. And the first thing it does is enable interrupts, STI, and then calls address 453, which is just a return call. It's fun. I don't know why they do that in some of these old programs. Just to call off somewhere and then immediately execute a return. And then it's setting up some segment addresses, stack segment, extra segment, data segment, etc. And eventually we get a call to 505, which is another return, and then 454, which is down here, which eventually calls 502. And again, we have another issue with, the byte boundary not being there, so we'll go ahead and hit that one too. And we'll do it again. All right, and then 502 calls and then interrupt 10, and then returns. Yes, that is setting the video mode. So up to that point, the system is just getting set up, and I'm not just going to stop there because it's just going to be more of the same, but it does set up the video mode. So as you can see here, though, the Pitfall 2 cartridge does not set up the interrupt 18 vector. It just jumps immediately into running and executing itself. So Like I said, I'll just stop right there as to not get down into the weeds. But at this point where I'm stopping here, it's setting the video mode that it wants, and presumably going to start getting graphics set up and everything else. So what we'll do next is we will move on to the basic cartridge, because I was kind of curious what that one looked like. So we're going to do similar again for the basic cartridge, although this time we know some of the offsets that are going to give us trouble. For instance, offset 3 and 9. And we'll go ahead and output that again and just take a look at what it does. And so again here, first thing it does is jump 0x23. And so we've got to add another one. And we'll do this again. Alright, and there we get to the actual start of the program here. So it does push the data segment onto the stack and clears out the AX register and does some other things. And what I believe this one is actually doing here is I believe this is setting up an interrupt of some form, setting it at an address of 0x60 and 62. But it is setting up some memory for it's putting the code segment and an address, this address 177, onto the interrupt vector table. And so what that means is eventually when this executes, we're going to come down to 177, and this is where this cartridge will actually start executing. And it's going to clear interrupts and start setting up some stuff. And I did look around this a little bit earlier, and what it seems to be doing is a whole lot of table entries set up. If I had to guess, it just looks like it's doing a lot of these kind of tabular type entries where it's moving a bunch of stuff around in a very repeated format. So I presume what it's doing is it's setting up addresses, and this looks like some sort of table where it's setting one of the registers and then jumping to another part of the code over and over and over again. So presumably what it's doing is setting up commands for BASIC to call directly into the cartridges. So presumably this would be for things for like the screen command, where the PCjr has additional screen command formats that the BASIC in the system, the regular BASIC in the system, does not understand. So this presumably is setting up additional allowances for additional video modes and other PCjr specific commands, like some of the sound and music commands, which do not exist on the regular IBM PC. So that's just a quick example of kind of what some of the cartridges look like. It wasn't quite what I was expecting when I took a look at them, but they do follow the format of what we're seeing in the documentation. And of course at the end here you can see this is I didn't show this earlier, but this is the CRC right here, the last 2 bytes. So for this particular cartridge it's 3CDD. The Pitfall cartridge ends up being 7407. So that's just the end bytes for the CRC algorithm. So let's go ahead and move on to how do we make our own cartridge so that we can do something interesting with this. Alright, so to start creating our own cartridge, in this example I just decided to start with Oscar Toledo's FBird program, which he has available on this website here. It's also available in his book, which is where I got it from. It does have to be adapted slightly to fit on the cartridge, but we'll get into that as I open it up. But here is the website, and I'll include that in the description below too, where he does have the source code available and a .com file too, actually, to run on like DOSBox or on an actual system too, if you'd like. So what I ended up doing here was setting up a version of this, and this is for NetWide Assembler, so if you're using MASM, it's going to be slightly different. Be very similar, but some of the way it formats things is different in the way that you set up segments and stuff. And especially the fact that, as I found out, the NetWide assembler is a little different about how you specify a far return versus a normal return. So anyway, but the program should look very similar to the one out of Oscar Toledo's book, except here we did have to set up the, or at least I chose to set up the interrupt vector for the interrupt 1.8 vector setup at the beginning of the program. So I did set up two different ways of the program being compilable. If you do a define for com file, it'll generate a .com, and if you do not, it'll assume you want a cartridge. So if you're not doing a com file, of course, that's where we get into, there's your headers right here for your 0550AA, and this particular program is two 512 byte blocks. Unfortunately, the original program is just like 1 byte too big for me to fit in one 512 byte block, including the header information. Because unfortunately the cartridge header information is slightly larger than the original header information in the original implementation. So I did have to extend it to an additional block. And then once, of course, you add up the interrupt 1.8 setup code, it gets even slightly larger. So anyway, so the length right here is, that's the 2, and here's the jump instruction for jumping to the code that is going to set up the interrupt 1.8 vector. And I actually had to add a no-op in here because this jump instruction is actually a short jump and therefore is only 2 bytes. So I just added a no-op just to take up that 3rd byte. And then, of course, there's your 00 from the header, which is also required. And then it just jumps into the code here. And I do want to thank Imperator Banana and Trixter on the Brutman forums for helping me solve some of the issues with this. When I first tried to run this program, I tried just doing it straight vanilla and jumping straight into the program and going, and everything looked like it was working and working fine until you press a key and nothing would happen. To make a long story short, what was happening is later on in the code in here, it is checking for a clock tick by calling interrupt 1A. Well, it turns out when your cartridge is first entered, at the very top, when it enters at this via this jump right here, while the BIOS is still checking through the cartridges, that it has not completely set up the system yet. And in this particular case, what had happened was the programmable interrupt controller wasn't set up yet, so the mask wasn't set up, and presumably other things probably aren't set up as well. But the interesting to note here, what we found out through digging in some and outputting some of the programmable interrupt controller mask was, like I said, that it was not set. So if you do it this method, which is with the interrupt 1.8 and then returning back to the BIOS to finish looking through the cartridges, you don't have that problem. The other alternative, of course, and there is an example, Imperator Banana put some code up on the PCjr Forums at brutman.com for how to set up the programmable interrupt controller. I don't have those here, but I will try to put a link to that in the description. And for the com file, I also did a enable interrupts. I don't remember why I did that anymore, honestly, but it may not be required, but I think it's just standard best practice. And then, you know, you do all the rest of your normal calls. So really, this is all kind of the header stuff for setting up either cartridge or .com file. And the only other thing of interest is at the very end of the program, you have to set up the CRC. And you could just hex edit this in yourself, and there's a couple ways to deal with it. But what I ended up doing here was actually setting up, I just told it to leave a to take the start of the program minus the end of the program, basically figure out the length of the program, subtract it from 1022, and that tells me how many bytes of blank space I need to insert at the end of the program before the CRC. So this is just filling in all the space between the end of the program here and where the CRC is, and then the last 2 bytes of the program are the CRC. So the question becomes, of course, well, how do you compute the CRC? I actually have kind of 2 ways here. I'll show you kind of both depending on how you want to do it. And I did want to point out one other thing I did find out in here is make sure, this is a mistake I made at first and took me a while to figure out, was when you do your first setup of the interrupt vector or the first call into your cartridge, make sure you do a far return. NetWide assembler, when you just say RET, does not make any assumption. It just assumes it's a short return, whereas the macro assembler bases it on your function definition, which will say proc near or proc far, which NetWide Assembler doesn't do. So the way they set it is differently. So in NetWide Assembler, you just have to explicitly specify RETF here so that it does a far return. Otherwise, you get some not right behavior. So CRC code, I did actually write a small program which can compute the CRC for you. And actually, before we do that, we need to actually assemble this. So let's go ahead and do that as soon as I remember the exact command. All right, so we're just going to assemble this using the NetWide assembler. Again, like I said, if you're using MASM, it'll be slightly different, and your code will be formatted slightly different. But the default is just to output a cartridge. If I want to output the com file, I just have to do a -d com file and output it as a .com, and that will, yeah. And I specified 2 outputs. Fun. All right, so there we go. We've got the .com file for it as well. So that actually generates the code. Now, as I said, you need to know what the CRC is. If you have to compile the program, at least the way I'm doing it, before you can know what the CRC is. So I wrote this program, which and I just specified an option to tell it to ignore the tail. So basically, this is just going to ignore the last 2 bytes of the cartridge I just generated. And if I run that, it's going to tell me that it read in 1024 bytes, so that's the size I expected it to be. And it's processing for the CRC calculation 1022 bytes, and the CRC is E14E, and that is what I have down here at the end. So if that didn't match, you would just update this and then recompile it, or go in and manually change it in a hex editor or whatever you wish, and you'll get the right values. Your other alternative for computing these is you can use this HXD program. This is a nice little free hex editor if you haven't seen it at all. I'll again provide a link in the description, but if I open the cartridge file here and select all except I don't want the last 2 bytes. So here I'm just going to select everything but the last 2 bytes and do tools, checksum. And for here, you want to select the CRC16 CCITT false is the one you want here. And in the selected data, not the whole thing. And that gives me out E14E, so that's the same thing. If you want to double check, what should happen is if you do the CRC with the last 2 bytes, you should get 00, which is actually how the system checks it, is it expects it to come out 00. So we just do select it again, and now we get 00. So that just checks out that the CRC is working correctly. But that is an alternative method to get the CRC if you don't want to write your own program to do it, or compile somebody else's, as HXD can do it for you. So once you have that, of course, the next thing you have to do is actually burn the cartridge. So in this case, what I have here is this is just my cartridge burner. It is a XGeku Pro TL8662 Plus. It's harder and harder to find these. I think it used to be easier not too many years ago, but more recently I had a harder time finding one. This seemed to be one a lot of people liked. So all I'm going to do here is take this. I'm going to take my EEPROM, and this is a Winballum W27E257. Important thing to note here is, like I said, if you're new like me, make sure you put it in the right way. It certainly matters. The dot needs to be on the top, and there's also a little divot on the chip that should match up, and just make sure that lines up on your top pin. Depending on the chip configuration, you could actually fry the chip if you tell it the wrong configuration. So this is the software that was provided with the with my TL866, and you can see here I've actually already got it set up for my chip, which is the W27E257. You just make sure you have the right chip selected, and I am going to tell it to erase, and we'll just tell it to erase the chip. It succeeded, so we're done. And then we need to load in the file that I want. I'll load in our cartridge file, and in this case we will just leave it to leave the default data in there. It doesn't really matter. Anyway, and there's our cartridge data. So you can see there's the 55AA02 for 2 512 byte blocks, and then the EB02 is the jump call. Incidentally, I didn't actually show this, but the HXD program is really nice for the fact that you can actually select like the byte here, and it'll actually show you what the instruction is for 16-bit machine language code and such, which is really nice if you want to see what a specific byte is, short of disassembling it. And if we go to the end here, there's our E14ERCRC check. Now, of course, this chip is much larger than it actually needs to be, so of course there's a lot of no data basically at the end, but it doesn't matter, it's not going to get used. The BIOS is going to check for up to 1024 bytes. It is going to hit that address, look for the CRC and it's going to stop there and say, okay, looks good, and it's going to go ahead and start. It's going to go ahead and call the entry function. So once we have that done, we hit the program button and we just hit program. And that usually doesn't take very long at all. It's going to verify it after it writes it to make sure that it reads back what it wrote. And that's it. You have a good chip at that point, presumably, assuming there's not any problems. One thing I did actually notice is there is this little check ID down here. One thing I did have experience is, since I'm relatively new to this and I don't have a stockpile of chips, I had to get some off of eBay. And some of them are more questionable than others. Some of them appear to have the wrong ID on them. So apparently the chip actually has an ID in it that is supposed to match this W27E257. Well, apparently some of the counterfeit ones might not, or it could, maybe that's not it. But my understanding from reading was sometimes the chip might not actually be correct, or could be a counterfeit. In which case you can turn this check ID off, if because you can still use the chip as long as it works. But that's, I think when I ran into a problem with one or two problems with this, I would just turn this off so that it would tell me the ID doesn't match. If you turn this off, you can get past that. Once we're done with that, you're just going to take the chip out of your burner and put it in the cartridge. And in this case, this is a 2-slot one. This is one I got off of eBay. And you do have to have the correct cartridge select and such set for this. And that goes back to the cartridge select settings before. I forget what I have this setting set to right now. It doesn't quite matter so much which one you set it to, so long as you pick one that's not already in use. Unless your cartridge has a specific hard-coded address expected in it. I don't know that a lot of them do that, but basically, yeah, just put your chip in, make sure you put it in the right way. I mentioned this before, but I kind of show this. This is Raphnet's cartridge. These are also really nice. This one can actually work with a 32 or 64K chip, and there is a little extra chip you can put in there so that I can actually select between the correct portion of the larger chip's memory, since the address lines can only address 32K normally directly. So with that, we should have a working FBird cartridge, and go ahead and check out and see how it runs on the system. Alright, and now that we have a cartridge burned with the FBird program, let's go ahead and try it out and see how it works on the system, now that we've worked the kinks out of it. And in a second here we'll get it to boot up, but I want to thank everybody for watching. I hope you found this informative and interesting. Please like and subscribe, and if you have any questions or comments, please leave them in the comment section below. And we'll go ahead and tell the system here to boot from cartridge, and here we go. Here's FBird, and it does actually play now, as before, and of course I wasn't paying attention, but it doesn't get stuck any longer, so we figured that issue out. So go ahead and after this you'll see when I have time, I will do a follow-up video on how the CRC algorithm actually works on the cartridge. I decided to go in depth onto how the BIOS routine actually worked, so I will create another video that goes into details on that, since that would make this video quite lengthy. So in any event, thanks for watching, and I'll see everybody hopefully again soon. Thanks.